Example 2. Draw the shear and bending moment diagrams for the beam. And this beam is subjected to distributed load. And this distributed load is not a uniformly distributed load. Instead, it is a linear distributed load. It increases from 0 at the left end all the way to 6 kN per meter at the right end. Step 1. Using the free body diagram of the entire frame, we're going to solve for the external support reactions. So I call the left end point A and right end point B. So at A we have AY, at B we have BY. And also I reduce the distributed load into one concentrated load, and the magnitude is the area of this triangle, which is 27 kN, applied at 3 meters away from point B. And after I apply the method of sections, I'm going to choose the left segment as the system of analysis. Therefore, I will only solve for the AY. So AY, based on the moment about point B, AY is 9 kN. So I'm going to place it on the free body diagram. This is AY. Now, since this distributed load extended all the way from the left end to the right end, so for this entire truss member or for the entire beam, the distributed load doesn't change, or the loading status doesn't change. Therefore, we can take the whole AB as the entire segment. So we don't have to separate, we don't have to do multiple segments in this problem. So we just need to section once between A and B. Step 2, we can write the shear and moment functions. To do that, we need to section the beam within each segment and draw the free body diagram of the left segment or the right segment. But in this case, since the distributed load extended all the way from A to B, the loading status doesn't change over the entire length of the beam. So we will just have one segment, segment AB. That means we only need to section once, any place between A and B, and then take the left segment to draw the free body diagram. Let's run an imaginary cut at an arbitrary location X from point A, and we're going to draw the free body diagram of the left segment. So again, don't forget the x-axis. Let's draw the x-axis on this beam as well. The x-axis is from the left end to extended along the axial direction of this beam. Therefore, it's from A to B. That's the x direction. And with point A, the left end at x equal to 0. And my imaginary cut is at an arbitrary location x from point A. So this is X. So now I'm going to choose the entire left segment to draw the free body diagram. So here's the free body diagram from point A. Here is a support reaction 9 kN pointing up, and the length of the left segment is X starting from A. And don't forget the distributed load. Again, that's a linear distributed load. So we're gonna put this triangle. First, let's figure out the distributed load on this segment on the original graph here. So based on proportional, because of proportional triangles, at point B, the loading intensity is 6 kN per meter, and we need to figure out the loading intensity at the cut at the right end of this section. So using trigonometry, the similar triangles, we can say x over 9 equals to, let's call this omega over 6. So I'm going to write the equation over here. 6x over 9 equals to omega over 6. So the omega, the loading intensity along the imaginary cut equals to 2/3x. So let's first place this smaller triangle on the left segment, and then we're going to replace it with one constant to the load, because we need it to write our equilibrium equations. So again, this distributed load increases from 0 at x equal to 0 to 2/3 times x at x. So the constant to the load that we're going to place will be located at 1/3 from the base. Therefore, it should be over here. So 1/3 of x to the right end should be 2/3 of x from point A. So put the location of this constant to the load on your free body diagram. Again, this is used to help you write equilibrium equations. Without this, it's not easy to write your equilibrium equations, and then it's not easy for others to interpret your work as well. So this will be 2/3x, and the magnitude will be the area of the triangle. So let's calculate the area of the triangle. So the constant to the load equals to 1/2 times the base, which is x, and times the height, which is 2/3x. So this constant to the load actually is 1/3x squared kilonewton. Okay, so those two are now our applied forces or external forces on this left segment. One is at A, 9 kilonewton. One is 2/3x away from A. The magnitude is 1/3x squared kilonewton. So don't forget, we are actually solving for the internal shear force and moment at the cut at the section. So let's place the internal forces at this place. I'm going to erase this one. So at the section, we will have a shear force V. Again, it's in the positive direction based on the sign convention, and there will be a N normal force, and since there's no x direction forces anywhere else, this N should be equal to 0, and there is the moment M, also a positive reaction based on the sign convention. So now we can write the shear and moment functions. From sum of the y direction forces equals to 0, we can solve for V. We have 9 minus 1/3x squared minus V equals to 0. So V is a function of x, which is equals to 9 minus 1/3x squared, and the unit is kilonewton in this given problem. Next, the moment about the sectioned end, which is the left segment, which is the right end at the cut, equals to 0. We are going to solve for the moment. So this will be -9. The moment arm is x plus 1/3x squared. Now the moment arm is 1/3x plus plus m equals to 0. We solve for m, so m is a quadratic equation or function, and m is a cubic function, and v is a quadratic function. And next, we can plot the shear and moment diagram. So to compare the result with the original loading status, I placed the original beam with 2 support reactions, one on the left and one on the right, and the overall distributed load on this beam. And now I set up the x-axis from 0 and the boundary is from 0 to 9 meters because that's the length of this entire beam. And the top one will be the shear force diagram and bottom one will be the bending moment diagram. So for the shear force diagram is a quadratic function. So you should be familiar with the diagram or the plot of a quadratic function. So this one, since the x squared has a negative coefficient, so it's an upside down one, we can find the boundaries for the v, meaning at x equals to 0 here, for the v, when x equals to 0 based on the function, v equals to 9. So we can put it on this point is 9. And at x equal to 9, the v is calculated to be negative 18 using that equation. Let's call it equation 1, and that's equation 2. So here the calculation is from equation 1. We find those boundaries. So it will be a negative value, negative 18, and the unit is kilonewton. So for the quadratic function, the shape is parabolic, something like that, right? It's not a linear, it's not a straight line, but it's parabol. So we need to figure out where the zero shear stress happens over the beam, which means when v equal to 0, what is the x value? Which is simple, right? Just to make the v equal to 0 means 9 minus 1 over 3 x squared equals to 0. Then we solve for x. And based on this equation, x is, we need to pick the positive value, isn't it? So it's 5.2 meter, which means at x equal to 5.2 here, the shear stress is 0, or this is the 0 shear point. From equation 2, we're going to plot the bending moment diagram. Since we already finished the shear force diagram, we'll do the same thing. At x equals 0, the bending moment is also 0. At x equals to 9, well, the bending moment is also 0. Well, how about between those two boundary points, between those two endpoints, how do we figure out the values of the bending moment m? Well, here is one equation I want you to remember. We will discuss this equation in more details later. This relation is between the shear force diagram and the bending moment diagram. So the shear force at a given x location equals to dm over dx. So which means the shear force is the slope of the bending moment diagram. So that is one reason why we want to see the zero shear. Where is the zero shear? We said at x equal to 5.2, the shear is 0. So when the slope is 0, well, the corresponding m value is either the maximum or the minimum, right? So recall from your algebra class, so when the slope is 0, then this function is either at its maximum or the minimum. So how to find maximum or minimum? That means, right, either it will be up here or down there, right? Maximum or minimum. So first of all, if you take a look at 0 to 5.2, the v's are positive because it's above x-axis. So positive slope means an increase, right? So the bending moment will increase from 0 to 5.2. Therefore, the bending moment should increase from 0 to some point, and at this point, again, when v equals to 0, the slope is 0. Then seems like the bending moment has a maximum value over here. And from 5.2 meter to 9 meter, the v values are all negative. Negative slope means a decrease in the m value. So m will decrease to 0. And we can also calculate the maximum bending moment because that's the value actually we are interested in. So how to find m max? Well, again, we know this m max happens at x equal to 5.2, so we just need to substitute x equal to 5.2 into equation 2. So the bending moment is calculated to be 31.2 kilonewton meter. And this problem is solved.